Aluminum bronze? Aluminium bronze? Aluminium bronze? Hello Internet, my name is Quinn and this is Blondihacks. I'm starting an awesome new extended project today. This is one that I've been really anxious to get going on, and I know a lot of you have been really waiting for this one. I got a whole big pile of copper here, and we are going to make a brand new boiler. This is going to be part of a steam plant for the PM Research steam engine that you saw me build over the past few months, and now it's going to get its own boiler. So let's go. Here's the engine that I'm going to build a boiler for, and well, let's start by just taking a listen to it. I gotta say, that just never gets old. Here's a boiler that I built several years ago. It's the first and only one that I've built, and it was also built from scratch. So you might be wondering, why don't people ever build boiler kits? If you've looked around, you know that while there are some boiler kits, they're pretty rare and much more rare than engine kits. And when you do find boiler kits, they're either very small or tailored to a specific engine that a manufacturer sells. And they're also all extremely expensive as a general rule. So if you're going to build a boiler, odds are you're going to end up building your own from scratch, like I'm doing here, and that means you're going to need to do some design work. A quick sidebar about units before we get in, because I know I'm going to get comments about this. All of the conversation here is going to be in imperial, and that's not because I like it. It's because all of the wisdom on building model boilers comes from old British books, and all the units in there are imperial. And a lot of this is magic fudge numbers that comes from experience, and converting those numbers to different units is fraught if you don't know really what you're doing. But I feel your pain on this. I'm happy to machine in thousands, but when it comes to real science, I want proper metric units, but that is just really not a good option here, so bear with me. Here's the boiler that I've designed and am going to build. Now, there's a lot of design work in this, and this is the end of a long research process, so I want to help you catch up to me here. This is a vertical fire tube design, and it's going to be gas-fired. I've only drawn one fire tube in the middle there, but there's 26 fire tubes, and it's 4 inches in diameter and 5 inches in height inside the water compartment, and the whole boiler is about 9 inches high. So I think it'll be a good fit for this engine. Visually, it's going to look nice, and if I did all of my math right, it should be very well sized to power this engine at full capacity. Okay, but back up a second. I just threw around a whole bunch of numbers, but how do you know how big a boiler needs to be for an engine, and how many fire tubes, etc.? Well, to understand that, let's boil some water, because it's helpful to understand what a boiler is actually doing and a little bit of the physics that go on inside of it. Yes, you've seen paint drying videos. Well, now you're looking at a water boiling video. I'll leave it to you to decide whether my narration is going to make this experience better or worse. So on this modern gas stove, it takes about 1.5 minutes from cold to get this water going to a nice vigorous boil. So that seems pretty good, right? Well, not really, because look at how little steam is coming off the top of this thing. Even while all this vigorous boiling, it's not even enough to dampen a paper towel, never mind run an engine. Furthermore, this is easy mode. There's no pressure on this pot. When you try to boil water inside a pressure vessel, the higher the pressure gets, the harder and harder it gets to boil that water. So I hope this gives you an appreciation of the amount of energy and the efficiency required to produce steam in such incredible volumes that an engine can consume it in real time at hundreds of RPM. So with all of this gas that we're burning, why does it take a full 1.5 minutes just to make this feeble amount of steam? Well, the answer is surface area. You can see that the heat is really only influencing the water around a narrow area at the bottom and maybe a little bit on the sides. So there's very little contact between the heat and the water, and thus very little surface area for transfer of energy. That's really what a boiler needs to do, is maximize contact of surface area between water and heat. Now notice what happens when I turn off the heat source. The boiling dies instantly. And that's an important lesson too. It takes an immense amount of energy to keep water at that boiling point so that it can keep producing steam. So we're talking about a lot of energy here. And I can immediately hold my hand over it and not get burnt. There's a little bit of water vapor, but no longer any actual steam production. There's basically three main categories of boilers. The first is the simplest, and it's the pot boiler. So this is literally just a shell full of water that you put a heat source under it, and it boils the water inside that shell. Now my electric boiler here has the heat source inside. It's an immersion heating element, but it's still a pot boiler. There's no fire tubes or anything in there. Typically a pot boiler is going to have some sort of heat source underneath it, and these types of boilers are pretty much always horizontal because that gives you the most possible area underneath to put fire. And once again, this is all about maximizing the surface contact between heat and water. And pot boilers are extremely inefficient because all you have is the little bit of boiler shell around the bottom to transfer that energy. So this is literally just a pot boiling on the stove. So the name of the game is surface area, and this is a vertical fire tube boiler that I'm going to build, and it increases surface area by filling the pot area full of fire tubes. So named, I suppose, because the fire is in contact with the interior of the tubes. So you can imagine if this whole area here is full of tubes, then you've got the heat source in the bottom there, and that heat is going to rise up through the tubes, and all the way along that journey, it's transferring that heat out the sides of all those little tubes and into the water all the way around. So that's much, much more efficient. Now, fire tube boilers can also be horizontal, and that's even more efficient because, of course, the heat wants to go upwards, and so it's traveling upwards through the water as the tubes are running horizontal. Vertical boilers are a little less efficient because a lot of the heat is just going straight up the tubes without ever transferring into the water. Thirdly, we have the water tube boiler, and here the tubes are full of water, as you might expect, and the tubes run through the heat source in some way. These are also immensely efficient. But the truth is, these boiler categories that I've described are very broad and fuzzy. For example, it's very common to have a fire tube boiler that has a few water tubes running through the firebox for a little extra efficiency. Then there's also things like flue tube boilers, which are kind of like fire tubes, but not really. And then there's flue return boilers and Scotch boilers. And there are more types of boilers than you could ever cover in a YouTube video. It's actually a very complicated topic, but these three broad categories will hopefully give you a sense of the options. So I've decided to go with the vertical fire tube design because it's the easiest to build of all of the more sophisticated boiler categories. A pot boiler is just so inefficient that it's never going to make enough steam to run my plant the way that I want to. So that was pretty much off the table. So it's really got to be a fire tube design. So the next question is fuel source. Barring weird outliers like electricity on my other boiler, your choices are basically gas or coal. Now you can also burn alcohol, or what the Brits call methylated spirit, in these boilers, but it's really inefficient and messy, so really you're looking at gas or coal. When we say gas, we're talking about usually camping gas, which is a mix of butane and propane. You can buy it at any camping store. To use gas, you need a burner. You've probably seen these. These are essentially just a log lighter like you would find in a fireplace with a ceramic mesh over top that creates a whole bunch of tiny little flames to evenly distribute the heat. And in this series, I'll be building one of these ceramic burners as well. And gas is really a much better choice for beginners. Managing a coal fire is very much a skill unto itself. There's a reason that fireman was a dedicated job on steam locomotives. But coal is capable of much, much more heat than gas. So if you really want to maximize the performance of a boiler and really drive real horsepower out of an engine, coal is the way to go. So if you want to go for coal, though, you got to think about that in your boiler design. With coal, the firebox is generally pushed up into the water tank effectively. So you've got water surrounding the fire on all sides. And that's not only for dramatically increased efficiency because you're really capturing all the heat of that fire, it's also a safety thing because a coal fire is much more difficult to control, and they can easily burn white hot and melt down the walls of the firebox if you don't know what you're doing. But this double-walled construction makes a coal-fired boiler much more difficult to build for a beginner like myself. Okay, topology and fuel source chosen. Now, how big does a boiler need to be for a given engine? Well, that is down to how much steam that engine is going to consume. Calculating the volume of steam that a given engine is going to need is surprisingly intuitive. You've got a piston moving back and forth in here, and this is a double-acting cylinder like most steam engines, so you have to fill this half of the cylinder and this half of the cylinder once each for each rotation of the engine. Well, this turns out to be a bit of simple geometry, right? Because we know the bore of the cylinder, the diameter of that cylinder in there, and we know the stroke of the engine. how much the piston moves from end to end, and we know the thickness of the piston itself, and so we can calculate what the volume is inside this cylinder at each end of the stroke. So to calculate the steam consumption, which is volume over time, we need to know what the RPM that the engine is going to be running at is going to be, so we know how many of those double cycles of steam we need to produce. Now, of course, engines run at all different RPMs, but you just want to size the boiler so that it will be comfortable driving the engine at whatever the maximum RPM is. Now, in this particular case, this kit has a suggested max RPM in the drawings of 250, so I'm going to use 200 RPM as my max because running an engine like this any faster than that is honestly just kind of crazy talk. And remember that steam engines don't need a lot of RPM. They produce maximum torque at 0 RPM, rather like electric motors. So it's not like a gas engine where you have to get a lot of RPM to get into some sort of narrow ideal torque band. You can run steam engines very, very slowly and drive whatever devices you might want to drive. And if you need to drive those devices at a specific RPM, like if you're driving a dynamo to make electric power, you can just alter the pulley sizes as needed to create the RPM on the device that you're driving. And the truth is you can simplify this a lot and just err on the high side of everything. Really, you can just take the bore, multiply it by the stroke, multiply it by 2 strokes per RPM, multiply by RPM, and end up with your cubic inches per minute of steam consumption, which for this engine comes out to about 471. So we need a boiler that can produce 471 cubic inches. But a boiler is less efficient the closer it is to its limit, so really you want a comfortable margin above that so that the boiler isn't strained to produce that much steam. But how have I gotten this far and never said a thing about pressure? Aren't boilers all about pressure? What about PSI and bar and whatever else? Well, pressure is important, of course, but it's also kind of arbitrary. So what you need to do is choose the pressure that you want to run your engine at and then design your boiler around that. However, there's a big catch here. This is a table of the properties of saturated steam. You can find this in many different books. And notice what happens as pressure goes up. Look what happens to production of steam volume. It goes down dramatically. This is basically the rocket equation of steam engines. So you know how rockets have this problem where the bigger they are, the more fuel they need to get off the ground, but the more fuel they have, the more fuel they need to lift the weight of the fuel that gets them off the ground. So it's this exponential losing curve, and steam boilers have this same problem with pressure. If you want to run really high pressures, it gets very, very difficult to produce any kind of volume. But the more pressure you have, the more power you can make. So it's really the pressure that's giving you your horsepower. So really you just have to choose a balance between how big your boiler is going to have to be to create volume at that pressure and how much power you want the engine to make. Now for a little engine like this, 25 PSI is plenty. I'm going to build this boiler to operate at 60 just because that's a convenient number for safety valves and so on. And that will be more than enough for a little engine like this. And make sure you know what your local laws are for building boilers because pressure is often a key deciding factor on whether your boiler needs certification and annual inspections. 100 PSI is frequently a cutoff in a lot of jurisdictions for what's considered a quote-unquote model boiler and what isn't. And I cannot speak for your jurisdiction. Every country and state and county and province has different rules regulating boilers, so make sure you do your research on this. I'll link below to a forum topic that has a lot of resources for finding out what the regulations are in your US state, and they also have info, I believe, on Australia and parts of the UK. But the other thing you can do is just Google your local boiler regulatory agency. Every area has one, and you can just email them and ask, how do you regulate model boilers, and what are the limits on size and pressure? This can also be dictated by insurance. If you ever plan to publicly display your boiler, the local model engineering association may have to inspect and certify it because otherwise they can't get insurance for your boiler to be displayed and operated in front of the poor unsuspecting public who may not know anything about your incompetence as a silver solderer. We finally have enough information to start doing some math and figure out the dimensions of this boiler. I made this spreadsheet to make it easier to play around with the numbers. So it's pretty simple. The top section has the geometry of the boiler, the number of fire tubes, the diameter of things, etc. And then that translates into the next section down. It does all the math to figure out what the interior volume of that boiler ends up being, including all of the surface area that's in contact with the water. And you generally calculate this with 2/3 full on the boiler because that's how they generally operate. There's a couple of magic numbers here. One is the evaporative power of the heat source, which is just a rule of thumb you can get from boiler design books that tells you roughly how much water can be converted to steam for a given square inch of surface area. So you multiply that by the surface area of your boiler and you get the amount of steam per minute that can be created from a given volume of water. And then the bottom section there is the engine geometry, which is just multiplied together to figure out how much the steam consumption is going to be. And then I can compare the steam production with the steam consumption, make sure I've got a comfortable margin there. And the cool thing is I can now play with these numbers. So what happens if I make the fire tubes an inch longer? Or what happens if I only have 20 fire tubes instead of 26? Or I might change the diameter of the fire tubes because I might not be able to get copper tubing in the sizes that I thought I could. That's a true story. I designed this boiler around 5/16 copper pipe for some reason, which turns out you can't really buy. So I was able to retweak all of these numbers just by changing my fire tube diameter. And then I did the same thing in Fusion to design this. I parameterized everything so I can say, okay, what does a 5/16 fire tube diameter look like? How does that affect the geometry and the construction? Or maybe I can go down to 1/4 and see what that looks like. And then I can experiment with the layout of the fire tubes. You know, maybe I only have 3 fire tubes on the center ring or whatever, because it's a little bit tricky to figure out how to lay out the fire tubes such that you have kind of an even distribution of them for different counts. So if you want to add or remove a single fire tube, you kind of have to redistribute them all evenly. So all of that kind of experimentation was made much easier with parameterizing everything in a spreadsheet and also in Fusion. And these spreadsheets and Fusion files are all available on my Patreon, so go check that out if you want to have your own little vertical fire tube boiler design kit. A quick note about material thickness, because you might be wondering how thick does all this copper need to be. You can look in the boiler design books and they'll have charts for how thick the copper needs to be for a given pressure. One thing to keep in mind is these books often come from the UK, which has a different gauge thickness standard than the US does, which nobody ever tells you. A 19 gauge copper sheet in the UK is quite a bit thicker than 19 in the US. So make sure you're looking at the actual measured thicknesses in millimeters or thousandths before you actually choose your gauge. And before you go and say, well, I'm just going to make everything super thick because it'll be extra safe, you actually don't want your tubes to be any thicker than necessary, because the thicker they are, the less efficient they are. And they don't have to be very thick because the pressure is on the outsides of the tubes where they're very strong. The shell needs to be quite a bit thicker because the pressure is going outwards on the shell where it's weakest. So keep that in mind. To construct all these tube shapes, you might be thinking, hey, can I just use copper water pipe? And the answer is yes. In fact, that's usually how this is done by hobbyists. The key, though, is that the books will tell you what wall thickness you need for a given pressure, but you can't actually buy pipe by wall thickness. You buy it by type or schedule, at least in North America. So copper water pipe comes in schedule K, L, and M. Those are a ratio of diameter to wall thickness. So the 3/8 fire tubes that you see on the left there are schedule L, which is a 30 thou wall thickness. Schedule M, which is like residential water pipe, would be 25 thou thickness in this diameter, which is a little too thin. Now the shell, on the other hand, is a 4-inch diameter of schedule M, the quote-unquote cheap stuff, and that's still a 95 thou wall thickness because of the diameter. The pressure doesn't care about the diameter, just the wall thickness. If you want to go larger than 6 inches, then you can no longer use water pipe, at least in North America. You can't buy copper pipe any bigger than that, and you're going to have to roll the shell, and you will end up with at least one seam. Creating a long pressure-tight seam in copper is not a job for beginners, so don't do that for your first couple of boilers. Stick to the copper pipe. One of the reasons I went to the trouble of doing a full CAD drawing of this boiler was so that I could really nail down all the materials I'm going to need. And this is what I had on hand. Amazingly, I had a lot of what I needed. So obviously some brass hex bar stock for making some of the external fittings on the boiler. For all the internal fittings on the boiler, that's anything touching the copper shell and the water or steam, that has to be bronze because that will suffer rapid dezincification otherwise. So boiler bushings and check valve bushings, anything that's going to be touching the boiler shell directly, that's going to have to be bronze. So for that, I have this really nice piece of aluminum bronze, and I like it because it's the exact diameter that I need for machining all of my boiler bushings and such. However, I don't actually know if it matters that it's aluminum bronze. So if you know, if you're more experienced in this sort of thing, let me know. If this is not acceptable, I do also have this piece of phosphor bronze, which I know is acceptable, but it's a larger diameter and this stuff is expensive, so I hate to machine all of this down for my little fittings if I don't have to. So yeah, I'll think about which of these I'm going to use. And then I've got some rivets here. These were actually donated to the channel recently, so thank you, Glenn, for those. And I've also got these beautiful pieces of copper for the tube plates. The reason I have these is because way back when I built my electric boiler, I bought extra of all the materials. I always try to do that. I always buy more than I need for every project. And then over time, you tend to have stuff on hand when you need it. So that's why I happen to have beautiful plates of copper just sitting in the drawer for years and years waiting for their moment to shine. And this is it. And then of course I've got some brass here for the smoke box cover. This is a little thinner than I was planning to use, but the smoke box cover is not structural, and so I think this thin stuff is going to be okay. And you know, I have it on hand, and brass sheet is also not the cheapest thing in the world, so I will use this since I have it. But now let's get to the good stuff. Look what the eBay man brought me. I have here some Schedule L copper water pipe for the fire tubes. Schedule L at this dimension has the wall thickness that I need. But now the real pièce de résistance. Here is a 4-inch diameter, 1 foot long length of Schedule M copper water pipe. Again, at this diameter, Schedule M has the wall thickness that I need, and this stuff, well, bring your checkbook. If you're gonna build a boiler project, get ready for some sticker shock, because copper is really obscenely expensive, especially at these diameters. And some of this stuff's a little hard to get, so all of this copper pipe is from eBay, partly because it's cheaper, but also because like the large 4-inch diameter stuff, which is like trunk line for cities and supply lines for high rises and stuff, that's actually pretty hard to get. The typical suppliers like McMaster and Granger don't have diameters that large. Some of the online sellers do have the large diameter, but they'll only sell you 3 feet of it, which is like $500 worth of 4-inch copper water pipe. So eBay is the place to go for this. Some of it will be in kind of unknown condition, like this piece here has some kind of a weird patina on it that I haven't seen before, but we make do. Okay, math done, materials gathered. I am ready to start building a boiler. I hope you'll join me for this whole series. There will be a playlist for it, of course, as with all of my larger projects. And if you want to support this effort, maybe you can throw me a little love on Patreon. There's a link down below and a card here on the screen. That really helps do things like buy all this expensive copper. Thank you very much for watching, and I will see you next time.